Alfred Wegener had a PhD in astronomy, but basically spent all of his time as a meteorologist, and he's most famous for his contributions to geology. Wegener's famous contribution is the idea that at one time all the continents were together as a single supercontinent, the continent of Pangaea, and that Pangaea broke apart and the continents drifted into their current positions. Wegener's climate research is what got him started on the idea of Pangaea, but it turns out there's lots of other evidence besides just the climate evidence. The fossil record is particularly interesting because if you go far enough back, you can find some of the same fossils on each side of the Atlantic Ocean. Also, the geologic evidence itself is pretty convincing. You can find identical rocks of the same age on each side of the Atlantic. And even more impressive is paleomagnetism. The Earth's magnetic field wanders. When igneous rocks form, they take a snapshot of the Earth's magnetic field at the moment that they formed. Therefore, you can tell where the North Pole was by looking at the rocks. In order to get the paleomagnetic data from different continents to agree on where the North Pole was, the continents had to have drifted over time. About 200 million years ago, Pangaea begins to break up into the subcontinents of Laurasia and Gondwana. By about 80 million years ago, Laurasia and Gondwana themselves began to break apart. Now, this breakup is a continuing process. Continental drift isn't something that just happened millions of years ago, it's an ongoing phenomenon that's happening today. Continents break apart to make smaller continents collide together to form bigger continents. It's an ongoing phenomenon. Laurasia broke apart to give us our northern continents. Gondwana broke apart to give us primarily our southern continents. But notice India. India nowadays is attached to Asia, but India started off attached to Gondwana. It peeled off of what eventually became Africa, slid over, and slammed into Asia. So not only was there a breaking apart, but there is also a coming together. It's an ongoing phenomenon. The big question that Alfred Wegener couldn't answer was, how and why do the continents drift? Nowadays we know that the answer is, in the upper mantle, the heat and pressure softens a rock, and the rock can flow over long periods of time. The top of the mantle and the crust we can lump together and call the lithosphere. Below the lithosphere we got the asthenosphere. And the asthenosphere is where the heat and pressure have gotten to the point where the rock softens, it can flow. So the lithosphere actually floats on top of the asthenosphere. We now realize it's not just continents that are drifting. It's actually large sections of the lithosphere. Call them lithospheric plates or tectonic plates. Anytime you've got a break in the lithosphere, you can have relative movements of the two pieces of the lithosphere. And this leads to continental drift. The breaks in the lithosphere are pretty easy to spot if you know what you're looking for. Volcanic ocean floor ridges, ocean floor trenches, other fracture zones like the San Andreas in California all mark plate boundaries. The plates can move three different ways relative to each other. They can move away from each other, we call this divergent movement. They can move towards each other, we call this convergent. Or they can move sideways relative to each other, and we call this a transform movement. And of course, there's all sorts of combinations of these movements. Divergent plate movement starts with a normal fault. If this movement continues long enough, the lithospheric plates will be completely separated, lava will well up, generating new lithospheric plate. In fact, this is exactly what's happening at a process we call ocean floor spreading. In the oceans, new plate is constantly being formed. The Atlantic Ocean is getting wider all the time. Remember from the previous chapter that the Earth's magnetic field changes and occasionally flips. It turns out that when lava cools, the orientation of the Earth's magnetic field is recorded in the rock. The process of ocean floor spreading records the history of the Earth's wandering magnetic poles. There are three types of plate collisions. Oceanic plate can collide with oceanic plate, or oceanic plate can collide with continental plate, or a continental plate can collide with another continental plate. When two oceanic plates collide, one of them undergoes subduction. It's pushed downward into the mantle, melted, and recycled. This pushing downward into the mantle generates a deep ocean trench on one side and a volcanic island chain on the other side. The islands of Japan were formed in this fashion. When oceanic plate collides with continental plate, the oceanic plate is thinner, and so it's always the one that undergoes subduction. Once again, that subduction of the oceanic plate leads to deep ocean trench and volcanic mountain chain on the other side, the continental side. A good example of this phenomena is the Andes Mountains. Theory of plate tectonics allows us to understand some otherwise puzzling features of the ocean floors. The ocean floors are relatively young compared to the continents. The ocean floors have thousands of miles of oceanic ridges and rises. Well, tectonic plate theory tells us those volcanic ridges and rises are divergent plate boundaries, new ocean floors being generated. This is why it's young. Also, why don't you ever find any old ocean floor? Well, plate tectonics says at convergent plate boundaries, the ocean floor gets recycled. Because continental plate is so much thicker than oceanic plate, it's much more difficult to subduct. So when continental plate collides with continental plate, you tend to get a lot more uplifting, folding and faulting. You get tall mountains being uplifted rather than a lot of subduction occurring. The Himalayas are a good example of this phenomena. India slams into Asia, generating the Himalayas. With the transform boundary, the lithospheric plates are moving sideways relative to each other. This is a type of fault we've got at San Andreas. In ancient times, people tended to think of the mountains and the valleys and the rivers as eternal, unchanging features. James Hutton was one of the first to recognize that the rock cycle meant that you've got continuous change. He called this cycle of continuous change. The rock cycle changes the face of the earth constantly. Charles Lyell took Hutton's idea of cycle of continuous change, modified it a little bit, improved it some, called it principle of uniform change. The processes that shape the earth are still shaping the earth. In order to generate an unconformity, first you have to have some rocks. You deposit some sediments, make some sedimentary rock, and since sediments collect in low places, if you're going to erode it, you're going to have tectonic movement first to raise it up. So tectonic movement raises it up, the rock now gets eroded, the rock now sinks back down, more tectonic movement, new sediments collect on top. And so now you've got layers of sediments separated by an eroded surface. It's good news and bad news. Good news is this unconformity tells you something about tectonic movements during that period of time. The bad news is any history that was recorded in the rock that was eroded is gone. In order to become a fossil, you got to stick around long enough to get buried and protected from erosion and preserved, which means things that are hard and tough, shells, bone, teeth, those are things that are the most common. Now, if you're going to have fossils, you got to have a source. Abundant life, rapid sedimentation are the keys, which is why your marine fossils are much more common than your terrestrial fossils. William Strata Smith was a surveyor and civil engineer, and one of the first to recognize that different rock layers have characteristic fossils. Nowadays we understand that the different ages of rocks have characteristic different fossils. The fossils allow us not only to know the ages of things, but also to know something about the climate and environment. After all, you don't have to worry these days about being attacked by crocodiles in Antarctica or the Mojave Desert. If you find crocodile fossils, you know that when that crocodile was alive, that area had to be relatively warm and quite wet. Before the 20th century, geologists could put relative dates on things, but not absolute dates. In the 20th century, we've discovered radio dating, and radio dating allows us to put absolute dates on things. Extinctions are used to subdivide the Earth's history into eras, and then the eras into periods, and periods into epochs. Extinctions are a reoccurring phenomena. Life appears to get going in the early Precambrian within about the first billion years or so. Simple marine bacteria, algae. In the late Precambrian, you begin to see simple marine invertebrates like worms starting to show up, and we also starting to get geologic evidence for the formation of a supercontinent. Our current eon started 542 million years ago. Following the Precambrian, we have an explosion in diversity of life. Trilobites show up, and then the true fish, the first vertebrates show up, and life moves from the oceans to the land with the land plants showing up, and later in the Paleozoic you get the amphibians, and unfortunately the insects, and then finally the reptiles. At the end of the Paleozoic, we have an enormous extinction event, one of the most thorough extinction events that we know of. In the early Paleozoic, large areas of the United States get flooded and dried out repeatedly. We also see evidence for the breakup of the Precambrian supercontinent into smaller continents. Later in the Paleozoic, well, more geologic activity, more advances and retreats of the shallow seas, and some of those smaller continents that broke up earlier are now colliding to form what will eventually become precursors to Laurasia and Gondwana. The Carboniferous period, which can be subdivided into Pennsylvanian and Mississippian subperiods, saw the advances and retreats of the shallow seas flooding huge swamps. Those swamps, once they're flooded, the plant material is buried under marine sediments, protecting those plant materials from complete biological recycling. Heat and pressure over time converts the plant material into coal. So a lot of our coal here in the United States came from the Carboniferous period. But remember, anytime the conditions are right, the Earth can make coal. So coal's an ongoing process. The Earth is making coal right now. The trick is, of course, we're using it faster than the Earth can make it. Because petroleum can migrate through porous rocks, you're only going to find large quantities of oil when it's trapped by an impervious layer of something like shale or salt. In fact, something like an anticline or a tilted fault's a great place to look because the oil as it's migrating along get trapped under that anticline or under that tilted fault. In the Triassic, you start seeing fossils of the first dinosaurs and mammals showing up, and also it looks like Pangaea is finally formed in the Triassic. In the Jurassic, you start seeing the first birds showing up, and Pangaea starts breaking apart. Cretaceous, start seeing your first flowering plants and your first pollinating insects as well. Also in the Cretaceous, Laurasia and Gondwana themselves are starting to break apart. And of course we have the famous extinction event that eliminates the dinosaurs. The current most popular theory for the extinction of the dinosaurs is an asteroid or comet impacting the Earth. The impact theory gets started in the late 70s when the younger Alvarez, a geologist, discovers unusually high concentrations of iridium in a thin layer of clay separating Mesozoic from Cenozoic rock. Since that time, other researchers have also found unusually high concentrations of iridium right at the extinction boundaries and other sites. Now, one of the things you'd like to find would be the crater. However, after 65 million years worth of erosion, the crater is not going to look much like a crater anymore. Despite that, there is a suspect area over in Yucatan that fits the bill. It's about the right size, and it's about the right age, and it's a shattered, heated rock area. In the Cenozoic, less of the continents have been underwater, so we no longer have the great shallow seas of the Paleozoic. However, we have had near constant volcanic and tectonic activity around the world. With the extinction of the dinosaurs, the diversity of mammals expands. In the Neogene, we see the continental drift creating the Red Sea and the Gulf of California. In the Neogene fossil record, we see the first modern humans as well as a number of extinct relatives. The Holocene has been an interglacial period, so we've had a relatively warm Earth. The history of the Earth has changed. The rock cycles reshapes the face of the continents, and continental drift moves the continents around. History of the Earth is also climate change, ice ages. It looks now that humans may be able to have some effect on the climate. In fact, we may already be having an effect on the climate with global warming. Human population, well, in theory we've got that under control. In practice, of course, we don't. Industrial development is another factor that in theory we could have under complete control, but seems at times to be out of control.